Welcome back. We're doing something a little different today. We're going straight into the deep end with a paper that I honestly think represents a foundational shift in how we build and align generative AI.
It really is a massive shift.
Right, so the paper is titled Direct Preference Optimization. Your language model is secretly a reward model.
Yeah, it's a catchy title, but don't let that fool you. This is a very dense, mathematically rigorous paper. It's coming out of Stanford and the Chan Zuckerberg Biohub So, Rafaelov, Sharma, Mitchell, and their whole team.
And the mission for our deep dive today is to really figure out if we can finally ditch the sheer complexity of reinforcement learning. Because, for the last few years, the industry standard for making AI safe, making it human-friendly for you to use, has been this incredibly complex pipeline called RLHF.
Right, and this paper basically comes out and says, you're doing it wrong. You don't actually need all that machinery.
Which is a huge claim. They're proposing a radical simplification.
Exactly. They are essentially saying we can remove the middleman from the alignment process entirely and achieve, well, better results with a stable, single-stage training process.
So before we get to their solution, which is this thing called Direct Preference Optimization, or DPOE, we really need to set the stage with the problem, just to make sure we're all on the same page.
Yeah, let's lay out the current context.
So we have these large language models, LLMs. They're trained on the entire internet unsupervised. They know a ton of broad knowledge, but they don't have a moral compass, right?
That's the core issue. An LLM is just a completion engine. It predicts the next token. So if you feed it a conspiracy theory, it completes the conspiracy.
Right.
If you ask it for code, it might give you buggy code because it has seen, plenty of bugs on GitHub. It has knowledge, but it doesn't have values. Or specific instructions on how to prioritize that knowledge safely, like knowing a misconception without stating it as a fact.
So we obviously need to steer it. We need alignment. And the current status quo, the method that OpenAI and Anthropic and pretty much everyone uses to turn a raw model into a helpful assistant, is RLHF.
Reinforcement learning from human feedback, which works. I mean, it is effective. But the paper argues that RLHF is essentially a computational and engineering nightmare.
Yeah, let's break that down. Because to understand why DPO is such a huge breakthrough for you guys building these systems, we have to understand the pain of the current method. Let's unpack the standard RLHF pipeline.
So standard RLHF is basically a three-step dance. Step 1 is the easiest supervised fine-tuning, or SFT. You take your raw wild model and train it on high-quality examples of instructions and answers.
Okay, so that's the foundation. You're teaching the model to stop just predicting the next word on a web page and start acting like a conversational assistant.
Right, but that doesn't scale. You can't write a perfect answer for every single possible question a user might ask.
Which leads us to step 2, reward modeling. And this is where the human preferences come in, right?
Exactly. You give the model a prompt, have it generate 2 different answers, and you ask a human rater which one is better, answer A or answer B.
To the classic A/B test.
Yeah, and you collect a massive data set of these comparisons. Then you train a completely separate neural network called a reward model. Its entire job is to look at a prompt and answer and spit out a numerical score representing how much a human would like it.
And the paper mentions they usually use the Bradley-Terry statistical model for this, right? To convert those A/B wins into a scalar score.
They do, yeah. So now you have a judge. You have the AI you actually want to train, and you have the judge AI that scores it.
Got it. And that leads to the final step, step 3, which is the reinforcement learning fine-tuning. And this is really the bottleneck.
Oh, absolutely. This is where you use an algorithm, usually PPO, Proximal Policy Optimization, to retrain the original language model. So the model generates text, the judge gives it a score, and the model tries to adjust its parameters to get a higher score next time.
And this is exactly where the authors of the paper say things just go completely off the rails.
Yeah.
Because now you are actively training multiple massive models at the same time.
It is so incredibly computationally expensive. Just think about it. Inside the training loop, you have to generate samples from the language model, which is fundamentally slow.
Right.
Then you have to run those samples through the reward model, then calculate gradients. And on top of all that, you have to keep a copy of the original reference model in memory just to ensure you don't drift too far.
Let's talk about that drift, actually. The paper specifically cites this constraint called KL divergence. Why do we even need a leash on the model?
Well, reinforcement learning is essentially just a maximization game. The model will eventually find a way to hack the reward. If the reward model slightly overvalues a certain word or phrase, say it really likes the word Furthermore, the language model will just start spamming that word to get a high score.
Oh, so just stop speaking actual English and start speaking reward.
Exactly. It generates gibberish that just happens to trick the judge. So engineers add a penalty term, the KL divergence penalty. It basically tells the model, maximize the reward, but do not stray too far from the probability distribution of the original model.
It's a leash.
It is a leash. And tuning that leash, deciding exactly how tight it should be, is incredibly difficult. If it's too tight, the model doesn't learn anything new. If it's too loose, the model collapses into that gibberish.
So just to recap the status quo for you listening, you have this complex three-step process. You're juggling multiple massive models in your GPU memory. You have a really finicky RL loop that is hypersensitive to tuning, and you have to constantly sample text during training. It works, but it's brittle.
It's a Rube Goldberg machine, and that is the exact context for this paper. The authors essentially stepped back and asked, do we really need the reward model? Do we actually need the reinforcement learning part at all?
And the answer, clearly, is no. Enter direct preference optimization.
This is the real aha moment of the paper. The authors looked deeply at the mathematical objective of RLHF. They looked at the equation that defines the optimal policy, the perfect AI agent under that KL constrained reward maximization I was just talking about.
And they found a relationship, a mathematical trick.
They found a closed-form solution. Essentially, they realized that if you have the optimal policy, you can mathematically derive the reward function directly from it. And conversely, if you have the reward function, you can derive the optimal policy. They are duals of each other.
It's a change of variables. So instead of training a reward model and then training a policy, they define the preference loss as a function of the policy directly.
Precisely. They inverted the math. Instead of the old pipeline, which is data to reward model to policy, they just go data straight to policy.
And this is where the title comes in. The policy network, the language model itself, acts as the implicit reward. Hence, your language model is secretly a reward model.
Exactly. By training the model to simply classify which answer is better, you are implicitly optimizing the exact same objective as RLHF, but completely bypassing the RL loop.
That is wildly elegant. It literally turns a complex, unstable reinforcement learning problem into a simple, supervised classification problem.
And that changes everything for stability. You don't need to sample answers during training anymore, which saves a massive amount of compute. You don't need to tune PPO hyperparameters. You just run standard gradient descent on a specific loss function, specifically binary cross-entropy.
Let's actually look under the hood of that mechanism. What does the model actually do during DPO training? Because it's not just basic supervised learning.
No, it's very targeted. The model takes a prompt and a pair of completions from the data set. One is the winner, the preferred answer, and one is the loser.
Right, the A and B from earlier.
Right. And the algorithm looks at the likelihood the model assigns to the winner and the likelihood it assigns to the loser. It then adjusts the weights to increase the likelihood of the preferred response and decrease the likelihood of the dispreferred one.
Now, you mentioned something earlier about importance weights in the gradient. The paper emphasizes this as a key reason why DPO doesn't just degenerate.
Yes, this is a crucial detail. It's not just a naive probability increase. The algorithm incorporates a dynamic, for example, importance weight.
How does that dynamic weight actually work in practice? When does it weigh an example heavily?
Think about a situation where the model is looking at a pair of answers. The human labeled answer A as the winner, but the model's current internal state thinks answer B, the loser, is actually much more probable. The model is confidently wrong.
It's basically hallucinating that the bad answer is the good one.
Exactly. In this specific scenario, the implicit reward for the loser is higher than the winner. The math of DPO naturally scales up the gradient here. It gives the model a massive correction. It essentially says, you are very wrong on this specific example, change your weight significantly.
And what happens if the model already agrees with the human preference? Say it already likes answer A.
If it already ranks the winner higher, the importance weight approaches 0. The gradient essentially vanishes. It tells the model, you got this one right, don't waste learning capacity tweaking things here.
So it automatically focuses all the learning capacity on the hard examples, the ones where the model's internal priors actively disagree with what humans actually want.
Correct. And this is what prevents the model from degenerating. If you just tried to maximize the probability of the winner without this specific weighting, the model would drift wildly. This weighting mechanism falls naturally out of their change of variables math, and it acts as the perfect replacement for that complex KL divergence constraint in PPO.
So the stability is literally baked into the math itself. rather than being enforced by some clunky external penalty loop.
Exactly. It's built right in.
Okay, so theoretically, this is a slam dunk. It deletes the middleman, simplifies the math, and stabilizes the training. But theory is one thing. Does it actually work when you test it?
They ran very extensive experiments to prove it does. They compared DPO against PPO, again, the industry standard, and the baseline SFT across 3 main tasks to see who came out on top.
And those tasks were sentiment generation, summarization, and dialogue. Let's start with sentiment. This used the IMDb movie review dataset, right?
Right. The goal here was to take the start of a movie review and force the model to generate a completion with strictly positive sentiment. This is a highly controlled setting because they actually had a ground truth reward function, a separate sentiment classifier, so they could measure exactly how well the models performed.
They mentioned the frontier in the paper regarding this test.
Yes, the frontier of expected reward versus KL divergence. Remember, ideally, you want high reward, meaning very positive reviews, but with low KL divergence, meaning it stays close to natural human language.
And how did DPO do?
In every single configuration, DPO dominated PPO. It achieved the highest reward while staying closest to the reference model.
So it was just vastly more efficient. It hit the goal without breaking the model's ability to speak normal English.
And here is the real kicker. DPO beat PPO even when they gave PPO an unfair advantage. They gave PPO access to the absolute ground truth reward function and tuned its hyperparameters extensively. PPO, with every advantage, still lost to DPO.
Wow. Okay, but I have to say, generating positive movie reviews is a bit of a toy problem. What about summarization? They use the Reddit TLDR dataset for that one.
That's a much harder, far more subjective task. They took forum posts and asked the model to write a summary. Then they compared the win rates of those summaries against the actual human-written reference summaries.
Let's hear the numbers, head-to-head.
DPO achieved a win rate of roughly 61% against the reference summaries. PPO, at its absolute peak performance, only hit about 57%. So it's a clear, statistically significant margin for DPO.
And finally, dialogue. This is the big one, right? Building chatbots. They use the Anthropic helpful and harmless dataset for this.
This was honestly the most damning result for PPO in the whole paper. In their experiments on dialogue, PPO actually struggled to even beat the baseline SFT model. It basically just treaded water.
Wait, PPO couldn't even beat the baseline? That seems shocking given it's the standard for ChatGPT and Claude.
It just highlights how unbelievably unstable PPO can be. If you don't tune the hyperparameters perfectly for the specific dataset you're using, PPO simply fails to learn. It's brittle. DPO, on the other hand, was the only method that showed significant improvement over the preferred completions in the dataset, and it did it with almost zero hyperparameter tuning.
There was another finding in the experiments that I think is crucial for anyone listening who actually deploys these models, the robustness to sampling temperature.
Oh yes, temperature controls how creative or random the model is. High temperature means more diversity in the output. Low temperature makes it more deterministic.
And usually RLHF models are notoriously brittle here. If you turn up the temperature to make them a bit more creative, their quality falls off a cliff.
Right, they turn into hallucinating poets. But DPO remained incredibly robust. Even at high temperatures, it kept its win rate up. PPO degraded rapidly, but DPO stayed stable.
Which implies that the probability distribution DPO learns is just much better formed. It doesn't just memorize a single best path. It actually learns a whole landscape of good answers.
Exactly.
That is huge if you want a model that can be creative and safe at the same time. Now, I want to touch on one specific experiment that really impressed me. Generalization.
The out-of-distribution test.
Yeah. They trained the model on Reddit posts, which are, let's be honest, chaotic, informal, full of slang. And then they took that trained model and tested it on CNN and Daily Mail news articles.
And DPO still outperformed PPO on the news articles. This is a critical finding because it shows the model didn't just memorize the specific style of Reddit summaries. It actually learned the underlying preference for how to summarize text effectively. And it could apply that fundamental skill to a completely different, much more formal domain.
Which is really the holy grail, isn't it?
Yeah.
Generalizable alignment. You want the model to learn the core values, not just parrot surface level syntax.
Precisely. It strongly suggests DPO captures the semantic intent of the human preference.
Now, I have to play devil's advocate for a second here. In these experiments, specifically summarization and dialogue, they didn't actually use humans to judge every single output. They used GPT-4 to act as the judge to determine the win race.
They did.
Is that a reliable methodology? Just Having the AI say the AI is good.
It's a very valid concern. It's a massive hot topic in research right now, but the authors anticipated this exact criticism. So they ran a validation study with actual human volunteers, mostly Stanford students and grads. They showed the humans the summaries and asked them to pick the winner.
And what do they find?
They compared the human choices directly against GPT-4's choices. And it turns out humans agree with GPT-4 about 65 to 80% of the time.
Is that a good metric? It doesn't sound perfect.
Well, it's actually about as often as humans agree with each other. Summarization is inherently subjective. So statistically speaking, GPT-4 proved to be a highly valid proxy for human evaluation in these specific tasks. It's consistent enough to validate the overall trend.
Okay, so the methodology definitely holds up. Let's zoom out a bit. What does this all mean for you, the listener, and for the field at large? We have this new method, DPO. It deletes the reward model, it deletes the complex RL loop, and it achieves state-of-the-art alignment using a simple, stable classification loss.
It essentially democratizes alignment. I mean, until DPO, doing RLHF well required massive compute resources, thousands of GPUs, and deep expertise in reinforcement learning, which is a very niche, highly mathematical subfield.
There was a moat. Only the huge labs, Google, OpenAI, Anthropic, could really afford to do it at scale.
Exactly. But DPO is computationally lightweight. You can run it on much smaller hardware because you don't need to load 3 different models into memory or sample text during training. It converges faster.
Which means university labs, open source developers, and smaller startups can now fine-tune models to their specific preferences without needing a $50 million supercomputer.
It's honestly like moving from coding in assembly to coding in Python. Suddenly, the barrier to entry drops significantly. We're already seeing this exact shift on Hugging Face. A huge portion of the top open source models are now using DPO instead of PPO.
It's quickly becoming the new default standard. And beyond just the practical engineering benefits, there's a really interesting philosophical shift here, too.
How do you mean?
Well, we've operated on this assumption for years that complex, value-aligned decision-making inherently requires reinforcement learning. An agent exploring an environment, getting feedback, and optimizing a policy. We treated alignment as a totally distinct process from basic learning.
Right, but DPO implies it's really just another form of supervised learning.
Exactly. It suggests that our whole understanding of reward in language models was maybe overcomplicated. We thought we needed this external critic, this separate judge AI. But it turns out the capacity to understand what is good or preferred can be baked directly into the model's own internal representation of language.
Your language model is secretly a reward model?
It really is the quote of the deep dive.
It is, and honestly, it leaves us with a really provocative thought for the future, something the authors themselves explicitly hint at in the future work section of the paper.
What's that?
If this direct preference method works so incredibly well for text, this idea that we can just skip explicit reward modeling entirely, could it eventually replace reinforcement learning and other generative modalities? Or is there a limit to how much we can simplify the concept of a reward?
Oh, wow. Like applying this to robotics or image and video generation.
Exactly. Think about a robot arm trying to learn how to grasp an object. Traditionally, that is a classic computationally heavy reinforcement learning problem. The arm tries, it fails, it gets a negative reward, it tries again, succeeds, gets a positive reward.
But could we frame that physical action as a simple preference pair, like trajectory A failed, trajectory B succeeded, therefore prefer B?
If we can, and if we can mathematically apply DPO to that space, we might be able to train physical AI agents vastly more efficiently. We might find that what we previously thought required these complex trial and error reasoning loops was actually just a preference optimization problem in disguise all along.
So the distinction between learning to know something and learning to act on something might be a lot blurrier than we ever thought.
That is the real frontier this paper opens up.
Well, whether you are training a massive LLM or just trying to keep up with the cutting edge of AI, DPO is a concept you absolutely need to understand. It's elegant, it's remarkably effective, and it is fundamentally changing the way we build and control AI.
Absolutely. It's rare to see a paper that actually clears the fog and shows us a much simpler path forward, but this is definitely one of them.
Thanks for exploring this with us. It's a dense topic, but a crucial one. Until next time, keep diving deep.